Today we're going to be talking about the unequal heating of the Earth's surface, or the troposphere. And that unequal heating is going to be due to three reasons, which I've written here. Now, in order to explain these three reasons, we need a diagram. So here's a diagram of the Earth. We've got the equator at 0 degrees. Now, let's assume that the sun is shining on the Earth, and the sun rays are coming in from this direction. Now, what I'm going to do is draw 3 rays at the equator, and then I'm going to draw 3 rays towards the poles. And we're going to use those 3 rays to help us understand what's going on here, why the Earth is heated in an unequal way. So, let's get started here. So, here's my first ray, here's my second, and my third ray. So those are rays of sunshine. And then I'm going to do the same thing up here at the top. This is going to be about 90 degrees up here. Right here, the top of the Earth is 90 degrees. And I'm going to do the same thing here. I'm going to have one ray come in right there, one ray below that, and another ray right there. So 3 rays of sun here, 3 rays of sun there. Now let's take a look at the first reason here. 1, variation in angle. All right? So you can see that there's a difference in angle here. And what's going to happen here is we have the Earth's atmosphere. Let me go ahead and draw the Earth's atmosphere, which is kind of hugging the surface of the planet. So that is going to represent the Earth's atmosphere. And you can see here, due to this variation in angle, that more atmosphere, these sun rays are going to have to pass through more atmosphere here compared to here. And as the sun rays pass through more atmosphere, more of the energy gets absorbed, and less energy actually reaches the surface of the Earth up there. Down at the equator, there's very little atmosphere for the sunshine to actually pass through. So very little gets absorbed, and most of that sun makes its way to the surface, where it heats the troposphere and where it actually heats the surface of the Earth. Now, number 2, the rays are distributed over different amounts of surface area. So if we look at this right here, I'm going to draw this line, and I'm going to draw another line right here. Here you can see the sun's rays. They're intersecting the Earth perpendicularly at a 90-degree angle. And here the sun rays are at an angle. And the rays are literally spread over a greater amount of surface area. Take a look at this compared to this. At the equator, the sun's rays are simply more concentrated, so you get greater heating. At the poles, the sun's rays are spread over a greater amount of surface area, and therefore there's less heating that actually goes on. Now, the last one has to do with albedo, all right, or reflectivity. That's what albedo means, the amount of sunlight that's actually reflected. Well, it turns out towards the poles, there's a lot of ice. There's a lot of white snow. And for anybody who's gone skiing, you notice that those sunglasses are very, very important because of the amount of light that gets reflected from that snow. In fact, about 90% of the light that strikes this ice and this snow up here, about 90% gets reflected. And only maybe 10% gets absorbed and heats the troposphere and heats the surface of the Earth there. Down at the equator, we've got a lot of dark-colored water. We've got a lot of dark-colored dirt and forests. So much more of the sunshine actually gets absorbed. We all know that darker colors absorb light. So here you've got about 10% of the light being reflected. 10% gets reflected. And this here you got 90% getting reflected. And only about 90% gets actually absorbed. So 90% reflected, 10% reflected, those are big differences. And that also contributes to the unequal heating of the Earth. Now, this unequal heating has big consequences. This unequal heating is going to lead to convection currents, mass movements of air. This unequal heating causes differences in pressure, which then lead to convection currents or winds. And this also creates varying patterns of precipitation. And we're going to talk about those topics in the next diagram right now. So I'm going to go ahead and I'm going to erase some of this information so we can draw some new information on our Earth. Let's draw our Earth back in there again. There we go. Now, let's go. We got 0 degrees. We've got the equator here. And I'm going to fill in the rest. This is going to be 30 degrees. This is going to be 60 degrees. And we've got 90 degrees. Same thing goes for south of the equator. 30 degrees. 60 degrees. And 90 degrees. Now, at the equator, as we just explained, we have very strong heating. So you've got a lot of heating going on here. And because of that, you've got a lot of warm air in this area. And this warm, hot air, in fact, this warm, moist, hot air, what happens to it? Well, hot air rises. So this warm, moist, hot air, we could call it, or moist, hot air, is going to begin to rise. And it goes up, 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 and it also goes up, up, up right here. Now eventually, as air rises, it begins to cool. It can only rise so high. It eventually cools and falls back to the Earth again. So it rises at about 0 degrees, and it falls back to the Earth at about 30 degrees south and 30 degrees north of the equator. Now, the same thing is going to happen here and here. We've got air descending here, and we can't have air ascending at the same time. So what I'm going to do is we're going to have a similar effect going on here and here. So air is going to rise and eventually fall back to Earth. Air is going to rise and eventually fall back to Earth. Same thing here. Air rises and falls back to Earth. Air rises and falls back to Earth. Make sure that your arrows are going the same direction. You can't have air rising and falling at the same time. So keep track of those arrows. Now, these air circulation patterns actually have names. Where the air rises at the equator and then falls at 30 degrees, in this area, this is referred to as a Hadley cell. So you've got 2 Hadley cells, one here and one here. Now above those Hadley cells, you've got 2 more cells of air, going from 60 degrees and falling back to 30 degrees. This is referred to as a Ferrel cell. Same thing here, Ferrel cell. And then up here, where the air rises and falls at the poles, we're going to call that a polar cell. Same thing down here, a polar cell. Now this rising and falling air has big consequences. Let's take a look at the equator here, and we'll look at those consequences. We have air, lots of hot, moist air rising up. Now because all these air molecules are rising up, there's less air molecules left below. So that creates a low pressure here. That creates a low pressure. And because air is falling here and here, this creates a high pressure. Think of all those air molecules coming down, descending, and getting squashed on top of each other. That creates a high pressure. So we've got a high pressure here where the air is descending here, Also, you get a high pressure. And down here or up here where the air is ascending and rising, you get a low pressure. A low pressure. And on the poles where air is descending, you get high pressure. High pressure. Now, let's take a look at this low pressure here, because we've got hot, moist air moving up into the atmosphere. Now, as that hot, moist air moves upwards, that air begins to cool. And we know that cool air can't hold as much water. So what begins to happen here is this water begins to get wrung out of the atmosphere. As that air cools, those water droplets begin to condense and fall back to Earth is rain. Lots of rain. So these low pressure areas are going to get a lot of rain. They're going to be very wet. Wet. And wet down here. Now where the rain falls back to Earth, we're going to have lush forests, like the tropical rainforest right here. Now, as the air goes up and it gets wrung out, by the time the air reaches its uppermost height, there's not a lot of moisture left in it. It's been pretty much wrung out, and by the time the air gets to its very highest altitude, there's not going to be a lot of moisture left into it. So when it begins to descend here, this air is going to be very dry. So right here where there's high pressure, wherever there's high pressure, we're going to have very dry conditions. Dry conditions. Even at the poles, very dry conditions. In fact, the poles, the North and South poles, are some of the driest places on Earth. Now, this has big consequences because these dry latitudes right here are sites of some of the biggest deserts in the world. The Mojave Desert in the southwestern United States, the Sahara Desert in Africa, the Kalahari Desert in Africa, the Australian Desert in Australia, and some of the deserts over in the Middle East are all near or on these high pressure areas, these 30 degrees latitudes right here. And the rainforest tends to be right here along the equator where you've got very wet conditions. Now, from there, you can see that we've got high pressure, low pressure, high pressure. We've got differences in pressure. That's going to create wind, because that's what wind is. Wind blows from high pressure to low pressure. So this sets up wind patterns. So we've got high pressure here, that's where the wind is going to blow out of. So I'm going to put a little dot here. And here's also high pressure. I'm going to put a little dot here. And we've got high pressure up here and high pressure down here. Those dots represent where wind is going to originate, because wind originates where there's high pressure areas and wind blows to where there's low pressure areas. So let's take a look at this. We've got high pressure here, we've got low pressure here, and high pressure. We would expect these high pressure areas, we would expect wind to blow into the equator, straight into the equator. But that doesn't quite happen because of something called the Coriolis Effect. It turns out that the Earth rotates, and as the Earth rotates, the Earth drags the air with it, and that actually deflects the winds. So what happens is these winds, instead of blowing straight into the equator, they get deflected sideways, just like that. And the wind gets deflected in this direction here, and this direction here. And the same thing goes for the poles. The wind gets deflected in this direction, and the wind gets deflected in that direction as it's moving from high to low pressure. And these winds have names. Now the nice thing is, there's a way to remember this. Winds are named due to where they originate. So winds are named from where they originate. So let's take a look at this arrow right here. This is a wind right here. This is a wind. And the wind originates right here in the northeast. So this is northeast of here. So the wind originates here and it blows here. So it originates in the northeast. So we're going to call this wind right here the northeast trade wind. And the wind down here originates from the southeast relative to this. So we're going to call this the southeast trade wind. And look at this wind here and this wind here. So the wind originates here and it blows towards here. So in a sense, it originates from the west. This is the west. So we're going to call this wind right here the westerlies. Same thing down here. These winds are called the westerlies. Lastly, we have the wind blowing out of the poles. And as you can see, the wind is blowing from the east. This is east relative to where it's blowing to. So we're going to call this wind and this wind the easterlies. Now, couple more details here. When you've got winds coming together or winds blowing away from each other, they're going to create areas that are extremely calm. So this calm area in here is going to be called the Intertropical Convergence Zone. Let's see, I'm going to do this with blue. Intertropical Convergence Zone. And it's an area right here, the winds converge. And the winds in this immediate area right here, where the winds actually converge, right in here, the winds in this immediate area are referred to as the doldrums. These winds are so calm, almost non-existent sometimes, that sailors of past feared these areas because their sailing ships could get stuck there for days or weeks. Same thing goes for 30 degrees north and 30 degrees south latitude. These winds, these areas right here, were called the horse latitudes. And again, the horse latitudes. Again, these areas were very calm areas in which sailors could actually get stranded for days or weeks. And if they didn't have enough water, sometimes, who knows, they might have had to throw those horses overboard in order to conserve water. And that's going to be it for unequal heating in convective circulation.